together into the region of supporting multiple packets sending together. Okay? So previous cases we have a sequence number 1 and 0. Now we will forget about 1 and 0. Okay? We will grow the IP. No, sorry, IP. I will grow the sequence number. Okay? So what is the number here? Okay? So as we grow, the expected number will keep changing. Remember, we always have a number that we expect. Previous case, first we expect 0, then we expect 1, 0, and 1 on the receiver side. And the sender side, we keep track on what is the next sequence number I should use. The first I will use the 0, then 1, and then 0, and then 1. Now the story change, total game change. We will start the sequence number with 1, and then we will keep adding 1 to the sequence number. And how about expected sequence number? Still do the same thing. Okay, so you start with the first packet with 1, and the second is 2, 3, 4, all the way up. Okay, so that's why I say one very technical point is that what is the data type for storing these two guys? Okay, and the data type determines the lifetime of the sequence, right? The sequence will eventually die when we reach a certain limit. Okay, how to tackle that limit, later on we'll talk about it also. So let's consider that the global n, the n, okay, of the global n protocol, we choose n to be 10 for the sake of the discussion. So what is the meaning of 10? It means at the same time, I can send 10 packets. Okay? Now, I will color the packets in different colors. If you see it is yellow, it's yellow here, yeah, yellow. Okay. If you see it's yellow, it means that a packet that sends but not yet acknowledged. Later on, you will see green. Green will be a sent packet with acknowledgement. Okay? So now I send out 10 packets. I mark the sequence number here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what is the next guy that I want to send out is 11. Okay? I cannot send beyond 11 because why? We have a governing n here. The n governs the width of the window. So the window width is 10. I cannot send beyond 10 unless I receive an acknowledgement saying that, hey, 1 has been received. Then I can move on and send 1 more. Okay? Then what's next? Next is we will have the sender side deliver all things into the receiver side. Let's consider there's no packet being dropped. Then we receive all things and they are all safe, no corruption. Then I will deliver all guys to the application layer. I deliver them to the application layer, and whenever I deliver one segment or one packet, I will generate acknowledgement number based on the packet that I received. So the methodology doesn't change. I send out sequence number 1 acknowledgement. It means that I received that guy. So I'll generate 1, later I'll generate 2, 3, 4, 5, 6, up to 10. Okay. And whenever I deliver 1 here, I will change the color to green to illustrate that this guy is being acknowledged already. And it is safe to be discarded. What is the meaning? Still remember, I say that there is a chance that some packet here already lost. Then I need to retransmit it. So whenever you find a yellow guy here, the yellow guy has to be stored in the kernel unless it's being acknowledged like this. Okay? So we have a chance that, all 10 guys arrive. Good. Very good. Then all turn into green. We can have a chance to go on with more packets to be sent. Okay? So can you see this is an improvement, right? Whenever I send 10 packets all arrive, then I can go on with next 10. As if I have a bigger piece of packet that I can utilize. Okay? So this is a throughput gain. Now, here comes problems. What are the problems? The problem is, what happens if packet 6 is being lost? Okay? So how can the receiver determine a packet is lost? How? Very simple, huh? First of all, receiver don't have any timeout. Okay? So how can I determine this guy is lost or this guy is missing? I will depend on this expected sequence number. Okay? when I receive 5, okay, save. So I generate a 5 ACK and deliver it to the other side, and I also deliver number 5 to the application layer. I get ready for the number 6. Number 6, where are you? Why I receive number 7? Why is this number 7? It's just because number 6 is lost, or I don't know why it go out of order. Okay? So at this particular moment is the moment that I know something wrong. And if it's really lost, the best story continue with this. Okay? This is the best story, right? All guys here color in red are all out of order. Not good. Not good. So how can I tell the other side that something is wrong? Okay, please compensate for it. Okay, the way to ask this guy to compensate for it is to tell him that, hey, I cannot receive 6. I cannot receive 6. You tell this guy, keep on telling this guy about the bad news. The bad news is, hey, I need 6. I need 6. I need 6. In order to generate such a signal, I will repeat the last ACK that I can receive normally. Okay, so here is a normal packet that I receive. This at normal, all color in red at normal. So I have 1, 2, 3, 4 abnormal packets. I will generate 4 abnormal ACK, and this abnormal ACK is an ACK carrying ACK sequence number 5 to tell the other side that, hey, I need 6. The previous packet that I accept is 5 only. No 6, no 7, no 8. Okay, I need 6. Okay, then it will keep on deliver. And now this is the very stupid move. Okay, what is stupid move? It is not just because I want to introduce a stupid protocol. It's an implementation need. Okay, the stupid protocol works in this way. If I find any out of order packet, I discard it. What is discarded? What does it mean of discard? I remove it from the kernel space. I don't deliver it to the application layer. Wow, colorful, huh? Yeah, you love it? Yeah, you don't love it, right? We don't need it, okay? We will discard it. And this is the implementation thing, okay? It is not because of I want to introduce something bad. Later on, I will tell you why there is an implementation problem, okay? So, here we go. Oh, by the way, before here we go, okay? So here is a bunch of packets being acknowledged, and because this are all discarded, before discard, okay, I will send out, hey, bad news. I need number 6, I need number 6, and tell you that I only receive up to 5. So I keep on having this half of the packet marked as green. So as you are green, that means that you are being acknowledged, so I can safely discard it. And I can move on with my window. The window say that I can accommodate n packets. I accommodate n packets. So then when I move on, I will send 10. Again, 1, 2, 3, 4, 5 is a thing that pending for acknowledgement. 5 more to be sent out. Okay, to keep the throughput as high as possible. Okay. So of course, if you are picky enough, okay, picky means okay. If picky enough, then you will find one big problem in this protocol. Okay, the big problem is protocol. If I have a lost packet, okay, think about it. Why I have a lost packet? Huh? Congestion, right? If I have a congestion, if this is congestion, then it is a stupid move to still keep on the same sending speed. Understand what I mean? If you have congestion, congestion means, what is a congestion? Huh? What is a congestion in Nathan Row? Too many cars, right? Now here, maybe if we have congestion, then we lost packet 6. And the sender don't know how severe the congestion is. It's only know that half of the packet already lost. Okay? And in this case, you still insist on sending so big chunk of data, you will lose another half eventually. If the congestion is still bad, okay? So later on, we will tell you about how to improve this strategy. This strategy is bad. How to signal back to the sender, hey, there is congestion out there. Please shut up. Please be conservative. Don't send so many things. Okay, we call it congestion control. Okay, so in a diagram, okay, I can illustrate what is the idea of a sliding window now. Okay, what is the idea of sliding window? Basically, there is a hidden window of width like this. Okay, whenever you receive a packet, okay, and I create some variables here, later on this variable will become a part of our state diagram. Okay, so what is the variables here? We have a base, the minimum number of the packets that I have sent, but without any acknowledgement come back. Is the base, and the next next sequence number. Next sequence number means that the largest segment or largest packet that I have sent plus 1. Okay, that means the packet that I will eventually send out carrying the next sequence number. Okay, and this color, what are they? Okay, I said that the green one, the light green one, will be the sent and also acknowledged packet. The yellow one is sent but not yet acknowledged. What are the deep green here? The deep green here is maybe the chance that I have a big chunk of data, but I just have finished sending it. Okay, I still have some space left inside my window, so I will say that these are empty slots. Okay, and we have two states for empty slots. Either we have arrived data but not yet sent, or if it's empty. Okay, so here I choose to have a arrived but not yet sent, as well as I have a arrived packet but not allowed to be sent because of this Windows control. This window control also have a N here, as in the previous example. Okay, so the basic working is like that. The basic working is in the sender, we implement this array. Okay, if I ask you to implement a sliding window protocol, then you will have this array. Okay, an array is an array of packets with numbers. Okay, and if the next sequence number is smaller than base plus n, so what is the meaning? It means that base plus n is the width of the window plus the starting point. Okay, so that means starting point and ending point. The ending point is bigger than the next sequence number. So that means you still have capacity to send out things. You still have capacity, then please send out new packets with sequence number equal to the next sequence and add it to 1. Okay? So that means we will have this scenario. This is a combination of two scenarios. The scenario is keep sending these two guys. Okay? Then what if I have 2 acknowledgements coming back? Then I will move this window. You can see this. Yeah, this animation. You see this animation? Hand menu animation. Yeah. Yeah. Okay. So you can see this slide. The window will slice by 2 slots. Okay, with this acknowledgement coming back, and the rule is very simple. If an acknowledgement arrives, let the sequence number on the acknowledgement is n. So I don't know which 2, but let's say this 2. I pick the 5. 5 now n equals to 5. Base will be migrating to n plus 1. Okay, so eventually I will receive 6. So 6 plus 1 is 7. Okay, now this is a very, very important rule. Very, very important rule. Okay, because it can solve many, many problems. Okay, and this is the big chart here. The big chart here. Now I give you a big question. That question may take you 2 minutes. Okay, the big question is that I said that this is an important rule, right? Where can you find this rule? Base equal to n plus 1, where are you? Here. Base equal to acknowledgement number plus 1. Okay? And this is even more important that this base, if the base is equal to next sequence number, that means that we don't have any pending data to send. So I stop the timer else I reset and we transmit, we start the timer. Okay? Now what is my big question? The big question is here. This scenario, this scenario. And I write down my requirement. My requirement is, wait a minute. Okay. Let me start this guy. Okay. Control 2. Yeah. This pop up. Okay. Control 2. Okay. So the requirement is this acknowledgement all gone. Okay. So I color it deep red here. Okay. And all this acknowledgement all being lost. Only one guy is being delivered. It's 10. Okay? It's 10. That means that in the sender side, all these guys are gone. Okay? Only 10 is being received on the sender side. Okay? Now are you clear with this? Okay? All acknowledgements are gone. Only 10 are being delivered and saved. Okay? I said already here. Oh. Yeah. Wait a moment. So let's go to the state diagram. Sorry about that. I mixed full screen. Okay? So based on this state diagram, okay, if I have this scenario, I wait for send 10 packets. And I don't know why only the 10 ACK has come back. Will I generate any retransmission? This question makes sense, huh? I lost all except the last one. Will I generate any retransmission? I'll give you 2 minutes. I expect you will discuss with your neighbor and look at here and oh, 2 minutes, can you follow this chat? Okay. Okay, so let me discuss all these 4 edges. Okay, this is rubbish. Okay, this is not about our question, right? This, when data is ready, it means that the application layer gives you something, and then you deliver it. And if obey the window control that I previously said. The window control say that if the base plus n is bigger than the next sequence, that means that the window endpoint is further than the next sequence number. You can still go on sending something. Else, you cannot send any packets. What's next? Timeout. I never say anything about timeout yet. Okay, so later I will patch this point. I want you to look at this entire diagram, particularly this state. That state with base equal to ACK sequence number plus 1. Tell me whether it will generate any retransmission. If I only have the last guy. Of course, there is an assumption. I only have 10 packets to send, no more. I only have 10. And I miss all ACK except the last one. The last one has made its way home. Give 2 minutes. I expect you to discuss. Yeah, only look at this stage is enough. Okay, give you 1 more minute. 3年唔好先俾人當我心知底可以望下，明唔明？Waterfall 嚟嘅。哎呀，錄緊。我俾人唔係俾我。All right? Who think that you will have retransmission? Who think that no retransmission? Okay, good. Okay, so let's pick you. So what is the reason? What is the reason? No retransmission.
He received the acknowledge with the sequence number 10. That means the receiver has already received the all segment whose sequence number is less than equal to 10. So he knows that the segment with the segment numbers smaller or equal to 10 is all being safely received by the receiver.
Good. So he already give us the physical meaning, not following this if then else. Okay. The physical meaning is he already said it very clearly. Acknowledgement, whenever acknowledgement N received and sender, it means that all packets with ACK of sequence number smaller than equal to N is being safely delivered to the receiver side. So this is a very strong protocol, right? How strong it is? One acknowledgement means more than its own packet. It means all my previous brothers and sisters already being delivered. Okay? No matter how many ACK is being lost, as long as we have a big enough number can receive by the other end. Okay? Then the other end will know that all things is being delivered. Right? Wow, very colorful. Huh? But one point is the timeout thing, right? And now that's why I say that I don't start with the timeout thing. First, let you think about the mechanism. Then we look at the timeout. Now the timeout has one very tricky point. So what is a timeout? The timeout starts with whenever the base is equal to the next sequence number. That means that the window is still n, but inside the window, I don't have any delivered packets or not any one of them being carried from the application layer to the transport layer, and this is the beginning. Okay, so this is the beginning of the protocol. And the beginning condition is like this, both are 1. Then I start the timer. Okay? Then I start the timer. Why I start the timer? Because I'm a sender. I need to guarantee the safe delivery of the packet. And after I start the timer, when I will have timeout or reset on the timer, timeout is very easy. That means that no ACK has arrived, then I will have timeout. Or I have ACK arrive, not corrupted, okay? And the number is bigger than equal to the base. Okay? Now, it means that any one of the packets that being sent will trigger the reset and the start of the timer. Okay? So that means what? That means that every acknowledgement is very interesting. Whenever I send one packet, I will start the timer. I send another packet, I won't reset the timer. Okay? It's based on the control of the timeout and the reset of the timer is based on the continuous flow of the network. So what's the meaning? Let's say I predict that the round trip time is 1 minute. I give it 2 minutes for the timeout so that I already accommodate any possible errors with one round trip. And if the flow is flowing in a wide rate, no any accident in between any nodes in any endpoints, so the flow will keep on going and going so that I reset the timer will be a good time whenever I'm receiving any ACK. So remember, it has to take some imagination. There's a flow. Okay, whenever ACK come back to my home, I will reset my clock Whenever one guy comes back, we set the clock again. Now, what happened if I lost most of the ACK? You will have a problem. You will have a problem. Although the ACK itself has a very strong indication that it means all the packets before that number are being received. And I tell you that they are all safe. Look at here. Because based on the flow, if the flow suddenly stops, you cannot receive further ACK. Now it depends on how long that timer is. Okay? So, I mean, you know, looking at networking is very interesting. Even if we look at a simple flow chart, I can talk about for more than half an hour. Okay, in every little details and little control. And remember, it's based on the strong flow. The flow is strong and never stop. Okay? Of course, you can stop the flow. How you stop the flow? It becomes the initialization values. No, I mean the initial condition. They both are equal. Then I can stop. Okay, so that means that whenever you deliver a very big file, you generate a very strong flow, and you, based on this strong flow, to keep on resetting the timer without any false positive timeouts detection. Okay, understand what I mean? So although I tell you about the properties of the ACK, don't forget about another competing factor, the timeout. Okay, and that's why the timeout, it seems to be a good estimate that you have to accommodate for more than one packet to go. Okay, so let's say that I have a one minute for round trip. Maybe the timeout is let's say 5 minutes to accommodate for 5. That is half of the window lost. Okay, so accommodate for this. But in TCP, they are not doing the same thing. Okay, any question you want to ask? Any questions? If no questions, then I will go back to the sender side. The sender side, I still have something missing. Okay, so what is this do nothing? Okay, let's take a look at this do nothing. What is that? Corruption. Yeah, we can have corruption. Corruption is easy. So what is this case? This case is when I receive an ACK, that ACK is not something expected. Good. Okay, but what is the value? What is magnitude? It is smaller than my base. So what is the meaning of smaller than my base? The ACK range is in here. This range is smaller than the base. So how come I will receive ACK with this range? How come? Oh, very simple, huh? It's because of the sender sending things, and the sender, let's say in the previous case, I missed the packet 6. I missed packet 6. So when I miss the packet 6, then what will happen? I will send ACK with sequence number equal to expected sequence number minus 1. So what is expected sequence? It will first start with 1. I expect sequence number 1. Then when I receive 1, I will increase it. We increase it with 1 into 2. I expect 2 now. I expect 3. I expect 4. And suddenly I miss 6. I will expect 6. You still send me some other things that I am not interested in. So what is not interested in? The data sequence number is not equal to expected sequence number. I not expected. Okay, I'm not interested. So it will keep on saying that no, I don't want it. I don't want it. I don't want it. Something smaller than the expected sequence number. And it so happened that, okay, sorry, wrong direction. It so happened that if I have delivered this guy, the receiver will give me ACK 6 in this diagram, which is before the base. Okay, which is before the base. So the sender receives something before the base. I will not respond it immediately. I know that this is something wrong. It is, something wrong. Okay, the sender feels something wrong. Why I receive some duplicated acknowledgement? Of course, there are some packet being missed. Okay, some lost packet already are going on. I don't do anything and pass the ball to the timeout. Okay, I said pass the ball to the timeout. So how about the timeout? Timeout is doing something horrible. For all packet base to next sequence number, that means all packets being sent but not being acknowledged, or we transmit. Or we transmit. Okay? So why the storage comes in this way is follow this idea. The idea is out of order, discard, and I request you to retransmit those out of order packets together with the lost guy. Okay? So that's why I have this control. Okay? Any questions? Wow, colorful, huh? That's why I said that you need coffee today. Yeah, I drink 2 before I come. Okay, one small bug. The small bug is, what happens if the first segment is lost? Okay, so what will happen? What will happen in the first segment? But let's say that I have 10 packets to send. First guy is lost. Then we will enter a very abnormal status. The abnormal status is, I will have this edge being triggered. Let's say I've missed the first sequence number, there's 1. Then I receive sequence number 2 data on the receiver side. What should the receiver side respond? The receiver expect 1. No, it's not 1, it's 2. So I send 0. Okay? So this is a small bug. The small bug means 0 is not a proper data, right? No data carries sequence number 0. Okay? But I mean a kind of abuse it. Okay? Abuse means that if you see 0, that means that something wrong again. Okay? So this is a small logical bug, okay? But in terms of implementations, it's okay. So that's why I never start the expanded sequence number with 0. If I start with 0, or 0 minus 1, or negative 1, okay, no, we won't have negative 1, okay? So now the go back end implements like this, okay? Let's say I have the starting scenario like this. I've minimized my thing, okay? I don't have so many space in the diagram, so I restrict n equal to 4, okay? And I send 4 packets at the same time. Normal case is when I send all things to this side, this window slides. Now take a look at this area. Okay, you can see the window slides when it's arrived. Okay, the receiver know that all 4 guys has arrived safely. Then I send out ACK. When all ACK are all expected, I will set the next SEQ, next sequence number, by adding 1, okay, to the ACK number. Okay, and it so happens that the biggest one is 4. 4 plus 1 is 5. So this is the base, the same as the space, and the sequence number that I want to send out next is also 5, so I stop the timer and move the window, slide the window again. And the storage goes on again, and again. Okay, like this. Any question for this? No question, huh? This should be okay. Abnormal case, segment loss. Oh, this will be colorful, huh? So what is the meaning of segment loss? Let's say we imagine that number 3 is lost. Okay, number 3 is lost. So will it affect number 1 and 2? No, it won't affect number 1 and 2. So number 1 and 2 will be sent out with ACK number 1 and 2. Then how about number 3? Number 3 is lost. Then data number 4 arrive. It is unexpected. I want number 3. Expected SEQ is 3. Sorry, you are not 3. I will only acknowledge up to the previously good segment. So this is number 2. So I send out ACK 2. And also discard this sequence number 4. So I put a cross here. Discard means that I don't want you. And that's why the window will stay in this place. Okay? This place means the window don't slide. Okay? Although I receive 4, don't slide. Then when the sender receives 1 and 2, some little magic happen. Okay? Can you see this window just slides? Because I received 2 guys. So the window slides. When the window slides, it's open up new area for 5 and 6. So why not we also send out 5 and 6? Right? When I slice, I also send out 5 and 6. You know, if I do this, okay, it will end up in a disaster. Yeah. It ended up in a disaster. These guys, when it arrived, still not free. Go to hell. Remove you. Okay, disregard. Reply with bad ACK. And no matter when you arrive at, okay, I don't want to throw it again, okay, because whenever you arrive, I will ignore you because you're not the one that I want. Okay, and then timeout, I will have this trunk of windows unacknowledged, not acknowledged. So I will be transmit the entire windows 3, 4, 5, 6 together. Okay, and send a whole bunch of data there. And let's say there is no further drop, no further loss, then this whole bunch of window will be accepted by the receiver. Then receiver window will slice. And then with the normal ACK, this data window will also slice. Any question you want to ask? Any questions? Okay, I think it's safe for me to stop here. Okay. Already very big chunk of information for you. Okay, and one of the information is that, hey, why we need to disregard this guy? We will answer you these questions in the next protocol called selective repeat, and you will understand why selective repeat is not going to work. Okay. So if you have any question, you can ask me or stay here to ask me. Okay. We will stop the class now. We will see you again on the coming Wednesday. Thank you.